In this lesson, we discuss two-sample testing. Imagine a researcher wants to check if the average glucose concentration in pre-diabetic patients' blood differs from 110 mg per deciliter. Then set up a null and alternate hypothesis, like this: H0 mu equals 110, H1 mu is not 110. After choosing a significance level, collecting data, and checking assumptions, then run the test, interpret the p-value, and draw a conclusion. This process is known as a one-sample test, which you are familiar with. Now, let's say that instead of comparing glucose concentrations to 110, the researchers want to find out if there's a difference in average glucose concentration between pre-diabetic patients and those with normal glucose levels. In this case, we're looking at two distinct populations, so we'll need a two-sample test. The procedure is pretty similar to a one-sample test, with a few differences that we'll discuss. We should first determine if the samples are independent or paired. Independent samples don't have a direct relationship with their values, while paired samples contain related values. An example of paired samples would be a crossover trial in medical testing. Subjects take one drug for some time, then switch to another drug, and the responses to both drugs are recorded. Each patient will have two related values, one for each drug, resulting in two paired datasets. It's crucial to identify if the samples are paired or independent when performing a two-sample hypothesis test, because this will determine the sampling distribution used in the test. Let's say we want to compare the means of two populations, like the mean glucose concentration in pre-diabetic patients versus other patients. We'll base our hypothesis test on the difference between the means. The null hypothesis is H0 mu1 minus mu2 equals 0. And the alternative hypothesis can take one of three forms, where we have a left-tailed test, a right-tailed test, or a two-tailed test. Note here that the null hypothesis states that the two population means are equal, while the alternative hypothesis indicates the possible relationships between them. The assumptions for testing the difference between two means are similar to those for a one-sample mean hypothesis test. We have a simple random sample from each population, and each sample is large, that is, n is greater than 30, or its population can be assumed to be normal. Let's consider an example. King Tut was an Egyptian ruler whose tomb was discovered in 1923. A legend claims that those who opened the tomb were cursed, shortening their lifespans. A study compared the lifespans of 25 Westerners exposed to the curse and 11 who weren't. Both populations are assumed to be approximately normal, and we'll use alpha equals 0.05 for our hypothesis test. The null hypothesis is that H0 is that mu1 minus mu2 equals 0, which is the same as saying that mu1 equals mu2. The alternate hypothesis is that mu1 minus mu2 is less than 0, or mu1 is less than mu2. Let's pull in the data and take a quick look at it. We'll use the t-test command in R, with the variable for the lifespans of those exposed to the curse as the first input, and the variable for the lifespans of those not exposed as the second input. We specify the type of test, here alternative equals less. Now there is a paired option in this test, but since our samples are independent, we won't use it here. Running the test gives us a p-value of 0.1649, which is not small enough to reject the null hypothesis. This means that we lack strong evidence to conclude that the mean lifespan of those exposed to the curse is less than those not exposed. It sounds like King Tut's curse might just be a legend after all. Let's consider another example. It is well known that boys grow rapidly between ages 12 and 14. We have a dataset containing the heights, in inches, of a sample of boys measured at age 12 and again at age 14. We want to test if the mean height increase is more than 5 inches, using an alpha of 0.05. Note that we have paired data here. Looking at the data, we see 70 entries, which is larger than 30, so the test assumptions are satisfied. The null hypothesis is H0, which states that mu1 minus mu2 equals 5, and the alternative hypothesis is H1, which says that mu1 minus mu2 is greater than 5. Now, since we have paired data, we need to include the paired equals true option in our t-test command. We're testing if the difference in means is greater than 5, so we also include the mu equals 5 option. Omitting this option defaults to a difference of 0. Okay, now let's run the t-test command with age 14 heights as the first input and age 12 heights as the second input. The mu equals 5 option and the paired equals true option are also included, as well as the alternative equals greater option. Here we find the p-value to be 0.03729, which is small enough to reject the null hypothesis. We conclude that there is enough evidence to say that the mean height increase is more than 5 inches. Let's go on to testing differences in proportions. Similar to testing the difference between two population means, we can also test differences in population proportions. Now, the assumptions for performing a hypothesis test for the difference between two proportions resemble those for a one-sample proportion test. We have independent, simple random samples from each population. Each population is large, generally about 20 times the sample size, and both samples contain at least 10 individuals in each category. We're going to jump into an example. A survey was conducted on Parkinson's disease patients. Of 164 randomly selected patients who regularly exercise, 76 reported falling within the previous 6 months. Of 96 randomly selected patients who didn't exercise regularly, 48 reported falling. We want to know if we can conclude that the proportion of patients who fell recently is different from those who exercise regularly versus those who don't. We'll use an alpha of 0.01. Now we've got two populations here. Let P1 represent the proportion of the population of Parkinson's patients who exercise regularly, and P2 represent the proportion of the population of patients who don't. We have X1 equals 76, those who exercise and fail, and X2 equals 48, those who don't exercise and fail. We also have N1 equals 164, and N2 equals 96. Now we can check the assumptions and we'll find them satisfied. In R, I'm going to create data arrays for the number of successes, and I'll call that X, and the sample sizes, and I'll call that N. We have X as a data array which consists of the values 76 and 48, and N as a data array which consists of the values 164 and 96. Now we're going to use the prop test command with inputs X and N, and the alternative two-sided. The p-value that we obtain is 0.659. With such a large p-value, we fail to reject the null hypothesis, meaning that there isn't much evidence of a difference in the proportions of patients who recently fell. Let's wrap up with a real-world example from November 2020, when people were eagerly awaiting COVID-19 vaccine trial results. Pfizer, the first company to produce a vaccine, presented their initial trial findings. The study enrolled 43,661 participants who were randomly split evenly between a placebo group and a vaccine group. Out of 21,830 individuals in the vaccine group, 8 became symptomatically infected with COVID-19. In the placebo group of 21,830, 162 became symptomatically infected. We'll perform a test with the data array X, which is comprised of the values 8 and 162, and N, which is comprised of the values 21,830 and 21,830. Our goal is to determine the strength of the evidence that the proportion of infected individuals in the vaccine group is lower than in the placebo group. So let's run the test. The p-value is extremely small, providing very strong evidence that the proportion in the vaccine group is lower than in the placebo group. Let me point out a couple of things here. Although the assumptions aren't formally satisfied, with only 8 in one category, the large sample size compensates for any issues that this might cause. Also, we often hear about the efficacy rate of vaccines. A vaccine's efficacy rate is defined as the risk among the unvaccinated group minus the risk among the vaccinated group, all divided by the risk among the unvaccinated group. All this times 100. Now note that the prop test command output includes the sample proportions. Let's let p hat 1 be 0.00036644682, the vaccine group's sample proportion, and p hat 2 be 0.0074209803, the placebo group's sample proportion. Then, the study's efficacy rate is calculated as p hat 2 minus p hat 1 divided by p hat 2, all this times 100, which we find to be approximately 95.06%, which indeed was the efficacy rate reported for the Pfizer vaccine.